Hello and welcome to iitiansgateclasses once again. So today we are going to solve this question. Today we are going to solve this graph again with the Dijkstra algorithm. The Dijkstra algorithm solves a problem, single source, shortest path. So there is a source given, which is right now here, it's A. And you have to find the shortest path in a directed graph with given edge weights from the source to every other node. For example, A to B, A to C, A to D, A to E, and A to F. What is the minimum path? Okay. So the Dijkstra algorithm says that first write down the direct path A, B, C, D, E, and F. Okay. So direct path from A to A is 0. Initially, we initialize all other paths with infinite. Okay, all other paths are infinite. We don't know. Okay, then we consider the direct edge. Okay, so direct edge from A to A we consider. So algorithm goes like this. In the first step, we write down A with 0. This is the source only. Source with 0 and every other node with infinite. So now out of all these, whichever is minimum, we will pick that one and consider that for path reduction. Right now, A to B is infinite, right? So we will consider that from A to B, what is the minimum path? Whether there exists an edge that can replace infinite or not. Okay. So minimum is A. So let's cut down A and identify from A to B. A to B is 50, right? It's 50. You can see that it's 50 here. And A to C is 25. A to D is 2, A to E is 3, A to F is 10. You can check here. A to B is 50, A to C is 25, A to D is 2, A to E is 3, okay, and A to F is 10. So these are the direct edges given from A to every other node. A. So what I'm writing here is, let me use some other color. What I'm writing here is the last node we have visited before reaching to E, the last node we have visited is A. Before reaching to D via like from A, last node we have visited is A. Now again we will repeat the same step. I'm taking too much space. There are so many steps right now. So let me erase this one. Now, which one is the minimum? D is the minimum. So let's eliminate D. Okay. Our motive right now is we have a path from A to B directly. Now, can we have a path via D, which is lesser than 50? Let's see. We have a path via D, which is, we have a path from D to D, where edge weight is 3. Edge weight is 3, right? So let's try to add 3 with this 2. If this is less than 50, we will replace it. 3 plus 2 is 5, and 5 is less than 50. So we will replace it. We'll say that, okay. Let's try 5 here. And we are going via A. Sorry, via D. We are going to B via D. Similarly, we will repeat the same step. A to D we already know. A to A is 0. You already concluded it. Okay. Now we concluded that A to D is 2. Okay, we concluded because once we are finding out the minimum one, we are deleting that node from our finding space, or you can say our algorithm space, such space, we are deleting that node. And we are concluding that from A to D, it will take 2 units only. Now using this conclusion that A to D is 2, can we find a better path with lesser cost for A to B? Yes, we found out. It's 5. Can we find a better path for A to C? Let's see. D to C is 1. D to C is 1, right? And A to D we already know it's 2. So we can write down 3 here and D here. We'll go step by step. Okay. and this we already eliminated. From A to E, can we have a better path with smaller edge weights? Right now it's 3. From D to E, it's taking 4. So the total is 6. The total is 6, right? So we don't have a better path. Let's repeat the same here. From A to F, it's 10. From A to F, it's 10. From D to F, it's 1. So it's 3, right? In total, 2 and 3. 2 and 1, 3. So we have a better path via D, which is 3. So we'll write D here. Because if we are going via D, it's taking only 3 units. If we are going directly from A to F, it's taking 10. Now we will do the same thing. We will try to find out the minimum one out of all these. Now there are 3 minimum, 1, 2, 3. You can pick any one and delete that. For example, we pick this one, C. If we delete it, we conclude that A to C will take 3 units, directly or indirectly. From direct edge or indirect edge, this is the minimum path. A to C is the minimum path. So now we will see that using this C, can we reduce the cost of any of the remaining one, which all are remaining? B, A to B is remaining, A to E is remaining, and A to F is remaining. Can we reduce the cost of any of these 3? Let's see. Okay, so we write down like we already concluded A to A to C, and A to D. Now we have to find out what will be the value for here, here, and here. Out of these 3, we will again have the minimum and we'll delete that one. So for A to C is 3. Let's see. C to B, there is no edge. So it's just the same. C to F, we have 3. Right? We have 3. C to F. Now C to F, we have 3. And A to F, directly or indirectly, we already have 3. So once we use C, it will say that A to C to F will take 6 units, not 3, 6. So which is greater than current. Currently is 3. It's 3, right? So we won't replace. So it will be the same. It will be the same. Let's talk about E. So C to E, it's 5, and A to C via D is taking 3, which is the minimum path. So total A is basically 8. 8 is greater than 3, so we won't replace anything here. We'll say that, okay, this is the minimum path. Now out of these 3, which one is minimum? Let's see, we can pick any of these 2. We'll pick E. And we conclude that we found a minimum path from A to E, which is taking 3 units, exactly 3 units. Okay. So now let's see. Using E, can we minimize the cost of B or E, B or F? Let's see. From E to B, there is no edge, so it will be the same. From E to F, we have one edge, which is 2. A to E is taking 3. A to E is taking directly or indirectly is taking 3. We already concluded it. Okay, so we will never consider E for the minimum path again. We already found the minimum path as 3. A to E is taking 3, and E to F is taking how much? 2. So it will be 5, which is greater than 3, so we won't replace. Here, this will be the same, and this will be the same. Which one is the minimum? This one, F will be the minimum. And we conclude that A to F. So whenever I'm deleting the node, then only I'm concluding that this is the minimum path or shortest path from A to F, which is 3. Okay. So if we have an edge from F to B, which is less than, you can say, total path from A to F to B, then we will replace it. So F, there is no outgoing edge from F. So we also found that right now this is the only remaining one. All other are already concluded. So we'll delete B also, and we say that A to B, the minimum path is 5. And what is the shortest path? You can follow up this via node. So it's via D, right? So A to B is A to D to B. This is the minimum path. So if you want to find out what is A to E, you can see that it's via A only. So it's the direct edge. A to E is the direct edge. What is the path for C? You can see that it's via D. That's why I was writing the node here. So it's A to D to C. This is the minimum path or shortest path from single source. Single source is A to A is 0, A to D is 2, A to C will be 3, A to E will be 3, A to F will be 3, A to B will be 5. All these are minimum or shortest path for a given source. Let's consider one more example. It will clear the picture for you. Okay. Let me open up my notebook. So let's consider one more example. One sec. Let me pause the video. Okay. Okay. So this is the given tree. A, B, C, D, E, and F. Okay. So from A to B, we have a direct edge with edge weight 6. From C to B, we have a direct edge with edge weight 1. Okay. From D to A, we have a direct edge with edge weight 2. From let's first write down all the edges outside, going outside from A. From A to C, we have a direct edge with edge weight 90. Okay. And A to F also, we have a direct edge with edge weight 88. Okay. And what else is going outside from it? That's it. That we have only 3 edges: A to B, A to C, and A to F from A. Then from B, we have only 1 edge, which is going directly to D. Okay, with edge weight 41. Then from C, we have 2 edges. One is to B with edge weight 1. One is to F. It's C to F with edge weight 10. Okay, so that's it for C. From D, we are having 1 edge to A with edge weight 2. 1 edge to C with edge weight 12. Okay, 1 edge to E with edge weight 50. And that's it. From E, we have 1 edge to C with edge weight 16. From E and E to B also we have 1 edge with edge weight 3. Okay, so it may confuse you. This is C to F, and C to F is actually 10. E to B is 3. Okay, and E to A also we have 1 edge with 4. Sorry. So E to A, we have 1 edge with edge weight 4. So that is the whole graph. Note it down. So in the next page, I will be solving this graph using Dijkstra algorithm. Then we will do the time complexity analysis for Dijkstra algorithm. A, B, C, D, E, and F. Okay. Initially, A to A is 0. Everything else is infinite. Whichever is minimum, we will eliminate that one. A to A is minimum right now. And we conclude that A to A is 0. Sorry. A to A is 0. Now, whichever node we have eliminated A. Okay. So we will see that from A, is there any path from B, C, D, E, F, which is less than infinite? If there is no edge, that will be equal to infinite. If there is an edge, we will see that what is the edge weight. If that is less than infinite, we will note it down. Okay. From A to B, we know that it's 6 via A. A to C, we have 90. We don't have any edge here. A to F, we have an edge with 88. Okay. You can see above. From A to C, we have 90. A to B, we have 6. A to F, we have 88. Only 3 edges are there, which are 90 is less than infinite. That's why we replaced it. 88 is less than infinite. That's why we replaced it. And 6 is less than infinite. Out of all these 3, which is minimum, B is minimum. So we say that A to B is concluded, and its path from A to B directly or indirectly is 6. Okay. So using this path, we will try to minimize every other path. Right now, we have these options C, D, E, and F. If we can minimize the current path for A to C is 90, A to D is infinite, A to E is infinite, A to F is 88. Let's see if we can minimize any one of these. Okay, let's see. A to C, B to C. We will see B to C and we will add 6 into that. B to C, there is no B to C. Okay, so it will remain same. B to C will remain same. Okay, B to C will remain same. Let me draw a line. Okay. B to C will remain same. B to D, so A to C will remain same. B to D, we have one path with 40 edge weight. 40, right? 41, sorry. Right now it's infinite. 41 plus 6, right? Because we are writing A to D. And B to D is infinite. B to D is 41. 41 plus 6 is 47. So 47 is less than infinite. So we'll write it down. Now B to E. B to E, we don't have any edge. So it will remain same. Infinite, 88, and A. Okay. Now, which is minimum? This one, D is minimum, 47. So we conclude that A to D is 47. It is minimum. We can't reduce it further. Okay. So dash, dash, dash. We will use this 46 now. Only we will look into this D. If there is a path from D to C, we will add 47 and we will see that if that is less than 90. D to C, we have a path with 12. Okay. And 12 plus how much with A to D? 47 is 59. 59 is less than 90. 59. Okay, which is less than 90. So we'll write that we are going via D. Okay. So D to E. D to E, we have path with 50. Okay, so 50 plus 45, 47 is 97 via D, which is less than infinite. So we write it down. D to F. D to F, we don't have any edge. So we don't care. It will remain same. So which one is minimum? This one is minimum, 59. So we conclude that A to C is 59. So using C, if we can reach to any other node and we add 59 into it and we see that that number is less than 97 or 88, we will replace that. Okay, C to E. Let's see, C to E. There's no node, there's no edge, sorry. So it will remain same. C to E will remain same, 97 D. C to F. C to F, we have 10. 10 plus how much? 59. It will be 69. 69 is less than 88. So we now, which one is minimum? This one is minimum. So we eliminate F and we say that A to F, we know the minimum path, which is 69. Okay. Now using this 69 means A to F. Can we reduce A to E? Can we reduce it? Let's see. From F to E, there is no edge. So it doesn't matter. There is no edge from F to E. So this is the last one. We eliminate this and we say that A to E will take 97. Okay. 97. So this is how we can calculate the shortest path from source to all other nodes. Now, the next challenge is time complexity analysis. So this is pass 1, this is pass 2, this is pass 3. Let me draw a line here. This is pass 5, this is pass 6, this is pass 7. So at each pass, we are eliminating exactly one node. So how many pass will be there? How many pass will be there? We will have V number of passes. Okay, let me erase this. Okay. How many passes we will have? N number of passes, N or V. V is the number of vertices. Number of vertices. How many vertices do we have? If we have V number of vertices, we will iterate this algorithm V times. Okay, at V times. Okay, and at each step, how much cost are we taking? At each step, what is the cost? At this step, we are basically deleting the minimum. If we are maintaining a min heap, deleting minimum and again rebalancing the tree or validating the tree will take log E, because sorry, we can say log V, not E. Log V and E are same, but we are saying that log V because we have V number of nodes. V number of nodes we have. At each pass, we have V number of passes. At each pass, let's talk about this pass. At this pass, we are deleting a node with minimum weight. So if we are using minimum heap, min heap, in min heap, the deletion takes order of log n. Here n is number of vertices, so it is log V. So what is the time complexity? V log V. But we are missing one more thing. We are reducing the keys also. Once we delete the minimum, we see that if whichever node we have deleted, if we can reduce the path, right? If we can reduce the path. So if we reduce path or decrease the key, how many times can we decrease the key? In all the passes, all the passes, how many times, like, let me write the question. In all the passes, how many times do we adjust the weights? Adjust the weights. Okay. In first pass, we adjust, you can say V minus 1 weights. In the second pass, we adjust, for example, you can consider V minus 2 nodes. But that is not the tool. That is not how you are going to calculate the number of adjustment. Or this operation is called decrease key operation. Decrease key. What is decrease key? For example, you have a min heap. I am just considering a min heap, a random min heap. So what our motive is? What is our motive? That how many times are we decreasing the keys? For example, if it's a complete tree, because in complete tree, there are more edges, there will be more adjustment. Okay. Initially, at first step, we will do V minus 1 adjustment. Okay. So we'll delete A and every other infinite value will be reduced. If A is connected to all other nodes, V minus 1 decrease key operation will happen. Okay. So in a single decrease key operation, what is the worst case time complexity? For example, if I reduce this to 5, this will go here, then here, right? So it will take log V time. Log V. Why log V? Log V is the height of the tree. If you remember the min heap, the operation after deletion, how that happens, we replace the last element, we put the last element on the root, then we do the adjustment, and it takes log n time. Log V time. Here V is the number of nodes. Okay. So if we decrease a key, what is the worst time we will take? We will take log n, log V. This is the worst time we can take to decrease a single key. But how many keys can we decrease? It's E number of keys that you can decrease. E is the number of edges. Number of edges. If you think intuitively, you will understand that why we are doing number of edges time at max decrease key operation. Okay. So at each node, once we delete a node, for example, here we have deleted B. See, try to understand this. If we have deleted B here, okay, to whomever we have an edge, we can reduce only those keys, only those node weights. So here, if you have seen that B cannot reduce E because there is no B implies E. B is not implies. Sorry, B to E. There is no edge. There is no B to E edge. Okay, there is no B to E edge, direct edge. So how many times B can possibly at max can do the decrease key operation in min heap? Decrease key operation means once I delete B, I found out a minimum path to B. Now can this minimum path lead to reduction of another path? For example, if I know that currently A to D is 60 and A to B, I concluded that it's 10, is if B to D, if there is an edge between B to D, then only a reduction of this A to D can happen. This 60 can be replaced only if there is an edge between B to D. Okay, so that is why if you considering B, now you can consider every other node. The reduction can happen only E number of times. E is number of edges. So there are two operations. First operation is deletion of minimum from min heap. You know that finding out the minimum in min heap is the easiest way. Okay, so that is why we are using min heap data structure so many times. So deletion of minimum from min heap will take log v times. Okay. Second operation at each pass we are seeing. At each pass we are seeing the first operation. And how many times we did this operation? We did this operation v times. So it's v log v. And second operation is once we delete a node, or you can say minimum value from min heap, it may reduce other values in min heap corresponding to nodes to whomever this deleted node have an edge. Okay, so if you talk about only one node, how many decrease key operation can it do? Decrease key operation you have seen in here, right? It takes order of log n, because if you decrease any node which is at the last level, it will take log v time, right? It will take log v time. So if we consider only one node, how many decrease key operation it can possibly do or lead to the decrease key operation? Number of outgoing edges it have. Okay, so B can lead to decrease key operation of to whom? B can lead to a decrease key operation of only one operation, B to D, because it have only one edge, right? So if you talk about A, it can lead to A1, 2, and 3, D, 1 and 2. So we can conclude that if we add all the decrease key operation, it will be number of edges. Okay, all decrease key. So we were talking about one node. If you consider all the nodes, number of decrease key operation equal to number of edges, which is E. And each decrease key is taking log v times. Okay, so we know that the deletion will take v log v, number of deletion are v, and each deletion will take log v. So this is because of deletion. This is because of decrease key operation. So what is the total time complexity? V log v plus E log v. Okay, so it's v plus E log v. This is the time complexity, and it's same as Prim's. Prim's algorithm works in the similar way. So Prim's algorithm will also have the same time complexity. That's why I try to explain Dijkstra algorithm, because it's easy to explain time complexity here. It may seem difficult for you, but try to understand the number of operations we are doing and each operation cost. We are doing v number of deletion, and each deletion in min heap, it will take log n time. We are doing number of edges, number of decrease key operations, and each operation takes log v times. That's why it's this much. Okay. Let's move on to the problem of Dijkstra algorithm. So there are some, some basic problem with Dijkstra algorithm. Okay, so we have to address that also. Okay, I lost my changes. So give me a minute only. Yeah. So if we have a negative edge weight, if we have a negative edge weight, Dijkstra algorithm may give us wrong result. Okay, let's consider an example. For example, we have A, B, C, D. Let's consider that A is the source node, A to B is 90, B to D is 5, C to D is also 7, A to C is 180, and C to B is basically minus 178, B to C is 200. Now let's apply Dijkstra algorithm. Note this graph and we will apply the Dijkstra algorithm here. A, B, C, D. A to A is 0, infinite, infinite, infinite. Let's consider direct edges. We have 90 here, 180 here. There is no direct edge to D. Okay, it's via A. 90 is the minimum. Let's delete and conclude that A to A is 0. So in first iteration, we deleted A. In A to B is 90. Okay. But is it correct? Let's see. If we deleted B, let's try to use B to reduce the cost of C. Okay. If you go back to the graph, and you can check that from B to C, it's taking 200 actually. So which is greater than 180. So now if you consider B to C, the A to C via B will become 290, which is far greater than 180. So we won't consider it. We won't replace. We'll say that, okay, 180. From B to D, it's 5. So we'll say it's 95, which is less than infinite. It's via A, it's via B. Now, which one is minimum? This one is minimum. And we conclude that A to D is 95. Okay, and can we reduce the cost? There's no outgoing edge from D, and we conclude that A to C is actually 180. But is it correct? Let's see. A to B is correct, 90. Let me write down here. A to B is correct, it's 90. But it's saying that A to D is 95. And first it's saying that A to C is 180. A to C is 180. It's incorrect. How come? What we can do, we can go to B. From B, we can go to C, B, and C. Okay. If you try to go like this 2 times, like we can go from A to B, then from B to C, then C to B again, and B to C. What will be our cost? Here it's 90, here it's 200, here it's minus 178. Okay, here it's 200. No, this is not the way. We can go like okay, sorry. A to B is incorrect. A to B is incorrect. Sorry. A to C, not A to C. A to B is incorrect. If we go via C, A to B is incorrect. So in Dijkstra algorithm, what we did was we deleted the minimum one in the first step, which is A. In the second step, we deleted the minimum one, which is B. And we concluded that A to B is 90. But if there is a negative edge weight, for example, here, and if you go like A to C, then to B, it will be 2, right? A to C is 180, and C to B is minus 178. If you add these two, it will be 2, okay, which is far lesser than 90. So A to B should be 2, not 90. A to C is also correct. Like A to C is correct actually. It's 180. But what is A to D? If you think manually, what you can do, you know that A to B is 2. A to B is 2. Then from B, if we go from A to C, then C to B, then B to D, how much cost will it be? Like 180 minus 178 plus 5, it will be 7, right? Right now it's showing that A to D, what we did, A to D is 95. And here we are saying that it's 7. Because there is a negative edge weight, and the extra algorithm is not made to consider negative edge weight. We are not talking about negative edge weight cycle where both of these are negative. We are saying that only one of them is negative. Only one of them is negative. Okay, and the extra algorithm also fails in negative edge weight cycle because it can't identify negative edge weight cycle. The extra algorithm can't identify negative edge weight cycle. Okay, so if we have a cycle like the C to B, B to C, and we have both the edge weights are negative, this is an invalid shortest path algorithm actually. The extra can't identify it. So there is one more algorithm, which is Bellman-Ford algorithm. Let me try to explain that. It will take more time actually compared to the extra. It will take order of V cube. Okay, order of V cube. The extra was taking order of V plus E log V. If we have like complete graph, we know that in complete graph, E is equal to order of V square. E is equal to actually V minus 1, something like this, or V plus 1. Okay, something like this, like order of V square, right? E is equal to order of V square. I'm not sure about this one, but it may be V plus 1 by 2 or V minus 1, but ultimately it's order of V square. So if this is a complete graph, in that case, it's actually order of V plus V square log V, and this can be considered as V square log V. Okay. So here it's V square log V, here it's V cube. So V cube is actually greater than V square log V. Okay. So Bellman-Ford, this is Bellman-Ford algorithm, order of V cube. I'm going to explain Bellman-Ford algorithm for now, okay, and close this lecture, but it will take order of V cube, which is greater than the extra algorithm, remember this. But Bellman-Ford solves a problem of negative edge weight. The extra algorithm cannot work on negative edge weight. We just have seen the example. Right here. From A to B, it's taking 90. Actually, it's showing us that this is 90. Actually, it's 2. 180 and 1 minus 170, 78 is added, then it will take 2. And A to D is also showing 95, but actually it's 7. If we go like this, right? If we go like this, A to D is 7, but it's showing 95 as per the Dijkstra algorithm. So let's see Bellman-Ford algorithm, which takes order of V cube. Okay. Okay, so this is the example. Here you can see the graph. Let me repeat the edge weight for you if you are not able to understand the arrows and all. We have an edge from A to B with -1 weight, A to C with weight 4, B to E with weight 2, B to C with weight 3, B to D with weight 2. Okay, then from C we don't have any edge. From D we have only one edge. It is D to B 1, and from E we have one edge, E to D -3. Okay, so the algorithm says that repeat this step. How many times do we need to repeat it? V times. Repeat this step. Okay, before repeating this step, initialize weight of each node. Here you can say that if I'm saying u to v, so u to v, u is a node, v is a node, and for example a to b, right? A to b. So here a is a node and b is a node. Okay. If I'm considering this edge, now look at this step. I will write it down more clearly. Okay, for v minus 1 times, we will do v minus 1 time, and vth time for one more thing. We will see that v minus 1 time repeat this step for each edge. Okay, for each edge, let's see what we will do. We'll say that if the edge is u to v, u is a node and v is a node. If the condition is distance, the current distance labeled on that node, the current distance labeled that on node v. Okay, for edge u to v, we are calculating the distance for v. The distance v is greater than distance u plus weight on edge uv. Weight on edge uv. If this is the case, then update this distance. dv equal to du plus w uv. Okay. If this is the edge, from A to B is the edge. For example, there is some edge weight like k, and we already have some edge weight here, node weight here. For example, we already calculated that we have some value. For example, weight. Let me try to write it. So we are going to repeat this step v minus 1 times, and in each step we will repeat this step for each edge. So let's consider a single edge, A to B. Initially this is infinite, this is minus 1, and this is 0. Okay, this is the case. Okay, so what is u? U is A here, v is B. We are considering u to v edge. Now we are saying that distance of B, if distance of B, for this AB edge, if distance of B is greater than distance of A plus weight of UV. Okay, so distance of B is infinite, which is greater than 0 plus minus 1. So infinite is far greater than minus 1. Okay. Then we will update this distance. We will say that distance of B will be actually this 0 plus minus 1, which is minus 1, and update it here. Instead of infinite, write minus 1 here. Okay. So we will do this for each edge in the first iteration, and we will do these iteration v minus 1 time. So let's iterate some of the iteration. Note this graph down. Remember this graph. Keep it handy, and we are going to iterate it. A, B, C, D, and E. Initially, this is the edge weight similar to the extra. Okay, and let's see the edges. Let's see the edges one by one. Okay, let's see edge AB. AB we have already seen that it will be for edge AB. Currently, we can see that B is minus 1, A is 0, A is 0, okay, and edge weight is minus 1. Okay, and the condition says that if D of B is greater than D of A plus edge weight UAB, then initialize it like this: D of B equal to D of A plus edge weight. And this is satisfied. We have already seen in the previous example, right? This is satisfied. So we initialize B to minus 1. Okay, so similarly, we have to consider all the edges. All the edges. all the edges. Right now we are considering only one edge, AB. Let's see edge AC. Okay, AC. Right now C is at infinite, B is at 0, and edge weight is 4. Okay. Then let's see the condition. We are going to calculate distance for C. D of C is greater than D of A plus edge weight of AC. So D of C is infinite, which is greater than 0 plus 4. Infinite is greater than 4. Then we will update C to 4. 4 here. Let's consider another edge, which is BE. BE. Okay. Now remember this. BE will be considered for these values. For these values. Okay. We will update this value in single go in next iteration. Next iteration. And how many iterations do we have? V minus 1 iterations. Now for BE edge. B is also at infinite, E is at also infinite. These values are considered in next iteration. In the current iteration, both are at infinite, and the BE weight is 2. Okay, so what it's saying that D of E is greater than D of B plus weight of EB. Update the E, which is infinite, is greater than infinite plus 2. We can't compare infinite like this, right? This is an invalid condition. So it will remain to infinite. Similarly, for all other edges also, this will remain to infinite. Okay. Now we have to iterate this step how many times? Like let's consider another edge, which is BC. BC, okay. Let's consider another as BC. Now in the next iteration, once this iteration is done for all the edges, we'll do one more iteration for edge BE. Okay. So let me erase all these things. I will write the answer and you can imagine the iteration once I write down the answer for BE. Okay, let's do it for BC. Sorry, not BE, BC. Let's do it for BC with some other color. BC. Okay, C is 4, B is -1, and BC is 3. So if distance of C is greater than distance of B plus BC, the distance of C is 4, which is greater than 3. Sorry, not 3. Distance of B is -1. Distance means distance from source. This distance indicates distance from source. It's -1 plus 3. So 4 is greater than 2. So this will be replaced with the 2 here in the next iteration. Okay. This is a very common example. You can find it on other platforms like Geeks for Geeks, GFG, Geeks for Geeks. Okay. So here it's 2, here it's -1, infinite, infinite. So if you keep on repeating this step, after a while, all the edge weight will propagate and they will settle down. They will settle down to something like -1. This is the answer. Okay. After few iterations, it will be 0, -1. Okay. I need to erase this. I'm writing down the final answer. Okay, 0, -1, 2, -2, and 1. Okay, this is the final answer. Shortest distance. Okay, so they may ask you some intermediate answer. You can give them by running this algorithm. They won't give you very large graph because for each iteration you have to consider all the edges. Okay, for each iteration, and that is costly. So we are doing v minus 1 iteration, and for each iteration we are considering all the edges, which is e. And at the worst case, where complete graph, we know that e is order of v square, so it's basically v minus 1 into v square, which is order of v cube. So what happens if, remember this, that if, note that if for any edge at vth iteration, this condition satisfied for any edge u tends to v, for any edge, if this condition satisfied, d of u plus d of u plus d of w of uv. Okay, it means that there is a negative, okay, edge weight cycle. So after v minus 1th iteration, edge weight, not edge weight, the node weight should not change. If these are changing, it means that there is a negative edge weight cycle. Okay, so in vth iteration, that's why you are going to repeat it for v times. Okay, not v minus 1 times. So v minus 1 iteration will give you answer if there is no like negative edge weight cycle, as we have seen here in the example, that if you have something like this, something like 10 minus 20 minus 30 40 50 and some 60 here, not 60, like you can write 20 here also. Okay, so in the first iteration you can say that after settling down, the weight may look like 10 from A to B. It will be for B it's 10, for C it's 20, for D it's something, for E it's something, right? But after v minus 1th iteration, if it still changes, if there is still a condition which satisfies this, it means that there is a negative edge weight cycle, because the C to B will always decrease, right? C to B will always decrease because it's minus 30. And again, B to C will decrease with minus 20. So it's keep on going, it's keep on decreasing the shortest path from A to C and A to B, even A to D. Why? If you go from B, if you go from, let me write down the path. If you go from A to B and iterate it here n number of times, then go to D, it will decrease. If you iterate it n plus 1 time, it will decrease further. Let me give you an example. For example, you are going to D without iteration, like simply like this. So A to D will be 50. Now let's iterate it few times, like 1 time. A to D will be 10 plus minus 20 plus minus 30 plus 40, which will be 0. Once you repeat in this cycle, it will be A to D will be minus 50. Once you again iterate it 2 times, then go here. So you go to B and iterate 2 times here, then go to D. A to D will be minus 100. So it will keep on decreasing. So this shortest path are not valid. And to identify this negative edge weight cycle, we run Bellman-Ford V number of times. And from V minus 1th iteration to Vth iteration, if some values are changing, it means that there is a negative edge weight cycle. Okay, remember this. So that's all for today, students. Thank you all for joining. And we are going to start dynamic programming. It's a very interesting topic. I hope you join me in the next lecture. And it's very important for interview purpose also. Okay, thank you all for joining.